Hey everybody, let's give this problem a try. It encompasses a lot of the topics from the past few chapters. So here we have some block here released from rest, then it slides down this ramp, and then the ramp has friction, and it goes and then bounces off the spring and then goes back up the ramp. Okay, but then the entire time it's sliding down the ramp, energy is being lost because there's work being done by friction. So let's give this a try. So what's the speed of the object at the bottom over here? Okay, so let's start with work energy. So there's work being done by friction, and that is messing with our energy conservation. If not for the work being done by friction, energy would be conserved, but it's not. Right? Because this is some negative value. So then this is larger, this is negative, so this is smaller. So we have less energy final than when we had initially. Okay. So this work by friction, and then how much energy here? So kinetic energy, 0, it's starting at rest. There's no spring connected here right now, so there's no spring potential energy. Gravitational potential energy depends where we pick the datum. So let's say we pick the datum over here. Okay, so then that means the block has gravitational potential energy, mg, some height h above the datum, which is 2 meters. Okay, so that's it. That's the initial. And then it goes down the ramp. That whole time there's work being done by friction. And then it smashes the spring. So when it compresses the spring to some maximum distance, what is the energy here now? So it's at the datum. So the gravitational potential energy is now 0. At the maximum compression, the block is at rest right at that instant. So the kinetic energy is 0. Right after, it's going to bounce and go back the other way. But at the instant the spring is compressed maximum, the velocity is 0. And then when the spring is compressed, it has spring potential energy. So 1/2 k, however much it's smashed, I'll just call it x, squared, where x is right here. We know the value. We also know the spring constant, 500, that looks like a typo, newtons per meter. So we know the spring constant. Okay, so what is known and unknown? Work by friction, we don't know. Mass, 10 kilograms. G, got it. H, 2 meters. K, 500 newtons per meter. X, 0.75 meters. So this is the only unknown. So solve this for this answer. Work by friction, we know it. Okay, got it. Known. Well, that's actually part B. So part B, what is the work by friction? Got it. Okay, what's the speed at the bottom of the incline? So let's do part A. So when it's at the bottom of the incline, what's happening? It's going this way, and then it smashes the spring. So from here to here, see how the horizontal surface is frictionless? There's no work being done by friction from here at the bottom of the ramp to here where it smashes the spring. So different situation, work by friction, there is 0. Okay, so then we're just going from here to here now. So right here, it has kinetic energy, 1/2 mv squared. It's at the datum, so the potential energy, the gravitational potential energy is 0. And it's not touching the spring yet, so there's no spring potential energy. So then that's it. Initial is this. Final, when it smashes the spring, still at the datum. So the gravitational potential energy is still 0. And then it's at rest when the spring is compressed all the way. So the kinetic energy is 0. And then the spring is compressed by some x. So the potential energy, 1/2 kx squared. Okay, what is known and unknown? We don't know the speed, mass, 10 kilograms, k, 500 newtons per meter, x, 0.75 meters. So this is the only unknown. We can solve for it. All right, so let's see, k over m, x squared, squared. All right, got it. There's part A. Okay, part C, the spring recoils, sends the object back toward the incline. What's the speed when it's over here? Okay, so it's going this way, goes toward the right, bounces off the spring, goes back toward the left. Now it's going this way. How fast is this? So from here to here, again, there's no friction. So energy is conserved. How much energy here? That's when the spring is compressed, 1/2 kx squared. And then is at rest at the datum. And then later on, it's over here going speed v, so that's kinetic energy. What is known and what is unknown? This is the only unknown. Solve for that. Okay, which happens to be the same as part A, which makes sense because it's going this way with some amount of energy, smashes the spring with some amount of energy, bounces back, and it's going this way with the same amount of energy. No energy is lost. Energy is conserved. So we were expecting that to be the same. Okay, then part D, it's going some speed over here, but then there's no way it can reach here, right? Because when it slid down the ramp, it lost energy. And now that it's sliding back up the ramp, it's again losing energy because of friction. So how high is this? Okay, so let's write that. So work by friction on its way up the ramp. Initial, final. Okay, so initially we are here at the bottom of the ramp with some speed. And then we don't know this yet. Work by friction. Let me just leave it like that. Initial 1/2 mv squared, and we know the speed right here. And then at the datum, no spring. And then final, at the highest, the speed is now 0. And then now it's above the datum, some height, h. So mgh. So this is what we're after. Okay, we have to talk about this work by friction as it goes up the ramp. What is the work by friction? Work by friction is minus that friction force, which would be kinetic friction, times whatever distance it goes up the ramp. So along the ramp, let's say some distance d. Okay, but friction is mu k times n, right? Coefficient of friction times normal force. How much normal force? Here's the block when it's on the ramp. So when it's going up the ramp, friction is this way, normal force is this way, and the weight is this way. Okay, so that's the free body diagram when it's going up the ramp. And then if I pick coordinates however I want, and let's take a look at the picture. Okay, so the angle is here. In the x direction, we got minus mg sine theta minus friction equals mass times acceleration. In the y direction, we have n minus mg cosine theta equals mass times acceleration, the y component. But since the block is only going this way, there's no motion in the y direction. So ay is 0. So that means n equals mg cosine theta. So look, that goes right there. So that means the work by friction is minus mu k mg cosine theta times d. All right, d cosine theta. Okay, and then let me just draw that triangle one more time. If the height h is here, the vertical height, the angle theta is here, and this distance is, say, d, then sine theta is opposite over hypotenuse. So in other words, d is h over sine theta. Okay, so then we can just replace that with h over sine theta. H over sine theta. Okay, so this goes here. So let me write that. Cosine over sine, I'll just write over tangent. And then the rest of it, 1/2 mv squared mgh, this is the final height. And then here's the issue. What is known and what is unknown? We don't know this. Final height. G, we know it. M, we know it. Speed, we know it from part A and part C. The angle, got it. We don't know this. We don't know the coefficient of friction. Okay, so that's a problem. However, right at the very beginning, when we did this, part B, we know this answer. We know this number. And when the block was sliding down the ramp, work by friction is exactly the same expression here. So let me jot that down over here. Minus mu k mgh over tangent theta. But this, we know this. What is known and what is unknown? We know the work by friction. We solved it right here. This is unknown. This coefficient of friction is unknown. Mass, we know. G, we know. This is the initial height. 2 meters. So if you take a look at this, the only unknown is the coefficient of kinetic friction. Solve for mu k. Now you know it based on when it was sliding initially. So this is known, right? So take this answer, and now it goes here. We know it. So the only unknown left is this final height. I just take this, move it on this side. Plus mu k mg h final over tangent, right? And then factor out h final. Okay, and then note that mass is non-zero, so we can divide everything by something that's non-zero. And then just take all of this and put it in the denominator here, and then you got the final height. Okay, so give this problem a try yourself, and then, keep practicing until you got everything where you understand it pretty well. And then let me know if you have questions about it. I'll see you in the next video.